actually see that sigma t blows up, right? If any eigenvalue then you can see that sigma t goes to like infinity, right? Second thing what you notice here is like if actually you want greater than, even if it is equal to minus half, you can still show that it blows up. But if all the eigenvalues of this A matrix are less than minus half, yeah, then this recursion is stable. Not only that, you can actually again using the stochastic approximation theory that I showed earlier, you can show that the limit is given by this. So I told you that the limit satisfies this, right? F bar of theta star is equal to 0, but assuming this is a 0 in sequence. So similarly, you can show that using the same theory there, you can show that sigma theta, the limit, I'll call this sigma infinity, so basically the limit of this sigma theta, sigma t will satisfy that the Lyapunov equation over here, right? So yeah, if you give me a problem which has like and you give me this A matrix, A to be equal to dou theta of F bar of theta star, then I can tell you what the asymptotic variance of your algorithm is. Yeah.
If t converges to theta star, why doesn't the variance converge to 0?
No, so variance, asymptotic variance gives you the rate of convergence, right? It's not the convergence of theta t to theta star. It's like asymptotic variance is it's here. And it's here, the limit of this. So theta tilde t can go to 0, but does not mean that this has to go to 0. This t plus 1, the scale thing. So if this goes to 0, what it's saying is like the convergence rate of this is like 1 over t, which implies convergence of theta tilde t at 1 over square root of t. So this is more like the rate of convergence rather than yeah. So that's the thing, like, so even in stochastic gradient descent you have this optimal step size and everything, but if you don't select the step size to be like a function of I think this eigenvalues are related to this Lipschitz continuity of the gradients and the convexity, strong convexity coefficient and everything else, but you don't know that in advance, right? So if you don't choose it properly, then you can show that the convergence rate is like not 1 over square root of t, and it can be like very, very slow. Okay. So yeah, that's it. Like so.
So if you can show sigma converges, that implies that theta converges, right?
Yeah, I mean, yeah. Like I assumed theta converges while deriving this, so I don't know. Yeah. I mean, I don't know if you can get a formula for.
Like, can you relate those two somehow, or is that?
No, this is definitely like.
To back out the parameters.
So, like I said, to prove this limit of, to obtain the formula for this limit of sigma t, I assume that theta t converges to theta star, right? If you can somehow prove that without assuming that, then I don't know, maybe it implies theta t converges to theta star. You know what I mean? So, but what this implies is like, even if somebody tells me theta t equals to theta star, and they want to know the rate of convergence, and if I can verify that sigma t converges to something that is finite, then I can tell that the convergence rate is like 1 over square root of t. Yeah.
You don't get to pick A in this example. It's like the problem structure.
Yes.
So what happens if you're in scenario 1?
Yeah. So.
What do you do?
Yeah. So yeah. Good question. So I chose the step size to be alpha t plus 1 is equal to 1 over t plus 1. Actually, I can write it here itself. Okay. If alpha t plus 1 is equal to, say, g over t plus 1, okay, g is some constant, then you can show that exactly using the analysis what I did, you can show that I'll call this sigma theta. I don't like sigma infinity. So if you use a step size alpha t plus 1 is equal to, say, g over t plus 1, you can show that if you want lambda of ga to be all less than minus half, g is something you control, right? You can always make g big enough so that so all the eigenvalues of a are in the negative left half plane, so you make g big enough so that you scale all the eigenvalues so that it's all smaller than minus half. Then you can show that the asymptotic variance satisfies this thing over here. Does that answer your question? Yeah. So again, you don't even have to stick to a scalar. You can show that if you can make g oh, I forgot a g square here. You can actually try this out, like using the same thing what I did. It's not difficult to show that this is true. Like you can just, yeah, it's straightforward. And you don't even have to stick to a scalar actually. If you can use a matrix gain capital G, so again this whole thing is in RD, okay, because this is RD. You can actually use a D by D matrix gain over here. Okay, and it turns out that then you get something okay. And if you use G is equal to minus A inverse, assuming that you can somehow estimate it or like you know it, then you can show that the corresponding asymptotic variance sigma star is oops. You can actually show this, and when I say and you can show that this is optimal. Optimal in the sense that sigma star minus sigma theta g is greater than or equal to, less than or equal to 0. And this is, if you use a matrix gain like minus a inverse, that's like kind of like Newton-Raphson, right? Has anybody heard of like this thing called stochastic Newton-Raphson? Yeah, so Newton-Raphson is for deterministic setting. We have something similar for stochastic gradient descent. So yeah, yeah, it's basically second order. Yeah, and it turns out that if you use a Newton-Raphson like algorithm, you get like optimal asymptotic variance. Yeah. So and it's and the variance is given by this over here. Okay. I think that's most of what I wanted. Oh yeah, the homework. Has anybody taken a look at the homework, the stochastic approximation problem? Okay. Yeah, I know you had the exam quiz, so so I think in the homework problem, it's a 1D example, right? So d is equal to 1 and d is equal to 1 in your homework example, and and you're actually doing Monte Carlo average, so a is equal to -1, I think, and the Lyapunov equation will look something like this: GA plus half into sigma theta square 2 times this plus g squared. So this is the let me I told is -1, right? So in a one-dimensional example, you can actually show that this is what the fixed point equation would look like, and if a is equal to -1, then you can actually get a formula for the variance sigma theta square this way over here. Okay. But you don't know sigma delta square, right? But you can estimate sigma theta square. Okay. It's like the variance of so what you do is you do Monte Carlo for a bunch of for any fixed anyway, for a fixed scalar gain g, you do the stochastic, you simulate the stochastic approximation algorithm, and you estimate the square root of t times theta tilde t for a bunch of times, say like 1,000 times or something like that, and you can actually get an estimate of this variance sigma theta hat square by like doing this histogram, and then you can actually find the variance. Okay, and what we want you to do is we want you to estimate sigma delta square using the estimates of the sigma theta hat squares, basically using linear regression. So basically what you do is you substitute g is equal to 1, you get some number which you estimate using like simulations, and then you want to equate it to this here, right? That's it. And then you theta hat square at g is equal to say 2, and then you can get this. So basically you just try like different values of g, and then you get different values for this formula, and then like different sigma hat theta square. This is something you estimate, right? And then the goal is to find sigma delta square. So that's your homework. Yeah. And you can actually show that this formula here, it looks like so this is how the variance sigma theta square varies as a function of g. So because a is -1 over here, the optimal scalar gain is g is equal to 1, which is minus of a inverse, which is 1. Or should it? Yeah. So, and you can show that it blows up, the asymptotic variance blows up linearly if you make g too big, and if you make it too small, it goes to like infinity as soon as g is smaller than or equal to half. So okay, I guess that's it. Any questions? Okay. Yeah.
Explain how we get g in alpha, or like do we plug in g equals alpha?
Yeah.
G here?
Yeah. I wrote, yeah, here. Alpha t plus 1 is g over t plus 1.
Okay, so that's the substitution.
Yeah. So yeah, if you're doing stochastic gradient descent, I don't think you use decreasing step size, right? Most people use constant step size algorithms, but there is theory for constant step size algorithms too, but it's not as, I guess a lot of people do hyperparameter tuning. They try different values of step sizes and then you just pick the best one. But if you're doing something like decreasing step size, my suggestion would be to like use G as big as possible, and then try to project it in the beginning, the parameters, and then you can like slowly decrease the projection, and then you can actually get finite asymptotic variance. Yeah. instead of like trying different hyperparameters or different. Yeah. Anyway, so yeah, that's it. Thanks. Any more questions? That's it, right? Okay. Yeah. Yeah. Yeah.